So in the second video, we'll go over an example of working out an uncertainty of a sum, and then I'll go through some examples of how to compute uncertainties of products and quotients. So our first example, let's consider mixing of two reservoirs having different concentrations of a contaminant. So the problem is mixing and our two reservoirs, let's say, are streams that have been contaminated with a bacteria. Let's say it's a type of E. coli bacteria. And so the equation describing the mixing would be that the concentration of the mixture is equal to the concentration in the first reservoir plus the volume fraction of the first reservoir plus the concentration of the second reservoir times the volume fraction contributed in the second reservoir. So defining our variables, Ca is the concentration of our bacteria, and that's given in terms of a measured value, or a most likely value, plus an uncertainty in Ca. And let's say those numbers are 3.1 plus and minus 0.5, and the units here, let's say, are in terms of an advisory level. So this indicates that the concentration is 3.1 times the advisory level, and plus and minus 0.5 times the advisory level. And we'll describe Cb in terms of the same units. Again, a measured value plus and minus a uncertainty. And let's say that is 0.5 plus and minus 0.1. So there's a slightly less contaminant in stream B. And Fa will be the volume fraction contributed from stream A, and Fb, let me give you the value of Fa, and that's equal to, again, that's equal, well, let's just say that's equal to 0.3, and there's no uncertainty in this quantity for now. And Fb is the volume fraction from stream B, and let's say that's equal to 0.7. So the total volume contributed is 70% from stream B and 30% from stream A. So we want to compute what C is, and we're going to compute it in terms of a most likely value based on our measurements, plus and minus an uncertainty. So our most likely value, C0, is simply the most likely value of the concentration of A times the fraction contributed from stream A, plus the most likely value of the concentration from stream B, plus the fraction from stream B, and that's equal to 3.1 times 0.3 plus 0.5 times 0.7, and I get a value of 1.28 for that quantity. So now the uncertainty, the square of the uncertainty, which will be an estimate of the variance of the total concentration, is equal to the squares, it's equal to the sum of the variances associated with CA and CB. So the variance associated with CA is the partial derivative of the concentration with respect to the concentration A times the uncertainty in A squared. So this is the variance due to CA, due to a uncertainty in CA, and we have to add the variance of the concentration due to the uncertainty in CB, just applying our general equation. And therefore, delta C is equal to the square root of that those quantities. And so, if we first look at the partial derivative of C with respect to CA, we just take the derivative of this whole function, allowing CA to vary, but assuming all the other variables are constants. So the partial derivative of C with respect to CA is just FA. So that's FA times the uncertainty in CA squared. And now we have to take the partial derivative of the total concentration with respect to CB. So again, all the other variables are assumed to be constant. We're just looking at the variation due to CB, and that partial derivative is FB times the uncertainty and concentration of CB, and that gives the square root of 0.3 times 0.5, and that whole thing is squared, plus 0.7 times 0.1 squared, and that gives an uncertainty of 0.17. So from this, I would say that C is equal to the most likely value, which is 1.28, plus and minus the uncertainty, which is 0.17. And before we finalize our answer, we have to make sure we have the right number of significant figures. So I guess I would say that the uncertainties and the values of F are reported in terms of one significant figure. Okay, so the product should be only given in terms of one significant figure. So we would write that as equal to 0.2 to get the significant figures right. And therefore C would be 1.3 plus and minus 0.2 in terms of the advisory level. So so our uncertainty is limited to one significant figure, so we round it up, and we're going to report the concentration at a precision that's at the same level as the uncertainty. And that would be our answer. So now let's look at a product. let's apply this equation to a product. So let's say our general product is, say, P is equal to A times X times Y, where X is one uncertain variable and Y is another uncertain variable. And let's say A is a coefficient. And so we know that we would say that P is equal to the most likely value plus and minus an uncertainty. And so P0 is just the equation with the most likely value of X and Y applied. And delta, sorry, this should be delta P, not delta Y. Hope you guys caught that. Delta P, again, if we apply our general equation, that's equal to the square root of the uncertainty due to X. So that's dP dx. It's evaluated at x0, y0 times delta x plus and that whole quantity is squared, plus the partial of P with respect to y evaluated at point x0, y0, delta y squared. Okay, so in this case, we see that the partial derivative of P with respect to x is AY, and we're evaluating that at the most likely value of y times delta x, and that's squared. And we have the partial derivative of the second term is the partial derivative with respect to y, and that's AX evaluated at the most likely value times delta y, and that's squared. So that's an example of how to compute the uncertainty of a product. And if we go with a quotient, we apply the same rule. We just have to remember how to take partial derivatives involving quotients. So here we have a quotient, let's say, is equal to AX divided by y. And so we have, again, we have Q0 is equal to AX0 divided by Y0. And the uncertainty in Q is equal to the square root of the partial derivative of Q with respect to X, evaluated at the most likely values, times delta X, plus the partial of Q with respect to Y, and so that gives this. So the partial derivative of Q with respect to X, again, we take the derivative of the function in which X is only varied, and A and Y in this case would be constants. So the partial derivative of AY times X is just AY, A divided by Y. The partial derivative of A divided by Y times X is just AY. And we multiply that, and we got to evaluate that at the most probable value of Y, or our measured value. And we multiply that by delta X squared. And now we have to take the partial derivative of Q with respect to Y. And this is, just to remind you, this is just AXY to the minus 1 power. So if we take the derivative with respect to Y when it's raised to the minus 1 power, we get a minus 1 times AXY to the minus 2 power. And so I'll put that on the denominator. And then we have to multiply by delta Y squared. Okay, and so I guess we would write Q is equal to the most probable value, AX naught divided by Y naught, plus the uncertainty, plus and minus the uncertainty, I should say, of, let's see, that's A over Y naught delta X squared plus AX over Y naught squared delta Y squared. And I took out the minus because when we square it, we get a positive value. Okay. So these are just examples of how to evaluate a quotient and a product, but you should definitely not memorize these equations, but you should memorize the general equation that we covered in video 1. So again, if there's a function of x and y are each uncertain, we evaluate the most probable value of the function plus and minus its uncertainty. This is due to the first variable, the uncertainty due to the first variable, and then we have the variance due to the second variable. Again, evaluated at the most probable values of x and y naught. Okay, and so this is the general equation for a function with two variables. We could write a similar equation in which x or f is a function of multiple variables, say n variables, and that's equal to f evaluated at the most probable values of each of those variables plus and minus its uncertainty, which again involves partial derivatives of each of those variables. Okay, so you can apply this to two variables and to n variables if needed. So what I'd like to do is close the video with an example, and I'm going to give you the example. If you want to follow the video to watch how exactly I do it, that's great. But if you want to just try it on your own, that would be perhaps even better. So the example here is, let's compute a density. If we have a measured mass divided by a constant times a characteristic length scale cubed. So this is equal to the mass divided by volume, and where L is equal to the characteristic length scale. Characteristic length of our, or I guess dimension of the body, the volume that we're measuring or estimating the density for, and that's given in terms of L naught plus and minus delta L, and in this example, let's say it's 6.0 plus and minus 1.0, I don't know, millimeters cubed, for example. And the mass is, actually, let's make this meters cubed. And so the mass is equal to m0 plus and minus an uncertainty in the mass, and we'll say that's 10.0 plus and minus 2.0, and let's measure our mass in kilograms, for example. And let's say our coefficient which is a function of the shape of our object, relates the cubed dimension to its shape. Let's just say that's 3.1. Okay, so this is the problem. And for those of you who want to work it out on your own and come back to the end of the video and check your answers, that'd be great. But for those of you who want to follow along, then here's I'll go through that example. So again, we have our density is equal to our most likely value plus an uncertainty. And our most likely value, excuse me, is m0 divided by c times L0 cubed. And for that, let's see, we get 10.0 divided by 3.1 times 6.0 cubed. And for that, I get 0.0149 kilograms per meter cubed. And now let's calculate the uncertainty. Delta rho is equal to the square root. First, we take the partial derivative of rho with respect to m times delta m squared plus the partial with respect to L times delta L squared. And so the partial derivative of rho with respect to m is just 1 over CL cubed. So we get a delta m over CL naught cubed squared plus, now the partial derivative of rho with respect to L is, so again, this quantity is equal to m over c L to the minus 3 power. So we have a minus 3 m over c, and then we have to subtract 1 from the exponent, so we get an L to the 4th in the denominator, and that's multiplied by dl. And when I plug in my numbers to that, I guess I'll just go ahead and do that. I get 2 over 3.1 times 6 cubed plus minus 3 times 10 over 3.1 times 6 to the 4th squared. And when I evaluate that, I get 0.0080, or 8 times 10 to the minus 3 power. Okay, and I guess, I guess my uncertainty involves 2 significant figures, so I better write that as 8.0 to make that 2 significant figures. 8.0 times 10 to the minus 3. So my final solution is rho is equal to 1.49 times 10 to the minus 2 plus and minus 80 times 10 to the minus 2. Sorry, that's not right. 0.80 times 10 to the minus 2. And I don't want to report my most likely value at a precision any greater than my uncertainty. So I would say, make that minus 2, I would say this would be 1.5 plus and minus 0.8 times 10 to the minus 2 kilograms per meter cubed. Okay, hope you got the same answer, and that'll conclude this video.